Hey, welcome back. In this video, we're going to discuss Turan numbers of cycles. In the past videos, we've seen a bunch of results about Turan numbers, and some of them have been related to cycles. But in this video, we'll go into detail about what is known about the Turan numbers of each cycle. The smallest cycle is just the cycle of order 3, C3. And in the earlier videos, we already saw what is the exact Turan number of this cycle. So we saw that the extremal function n comma C3 is the floor function of n squared over 4. This is known as Mantle's theorem. And when we saw this in an earlier video, we saw it stated in a slightly different form. It was stated as ex of n comma k3 equals the floor function of n squared over 4. And this is equivalent because k3 equals c3. They're both this triangle graph. Another result that we saw, which is related to Turan numbers of cycles, is this upper bound, which is known as the Kovary-Sos-Turan theorem. So if you have a complete bipartite graph with parts of size r and s, all possible edges between the parts because it's complete bipartite, we saw how to prove using Jensen's inequality that the Turan extremal function of n comma krs is big O of n to the 2 minus 1 over r. By symmetry, we also have the upper bound big O of n to the 2 minus 1 over s. So we use the upper bound for the smaller of the two values. So if r is smaller, we use the upper bound n to the 2 minus 1 over r. And if s is smaller, we use n to the 2 minus 1 over s. And if they're the same, then these bounds are the same. When we have r equals s equals 2, this is a special complete bipartite graph. So we have our left part here, our right part here, and all possible edges. And we can take these bottom vertices and we can just move them around. So move them around in the plane. We can just swap their locations, but keep the edges still going to the vertices that they were going to. And that gives us another way to draw this graph. When we swap the location of those vertices, K22, so K22 right here, it becomes more obvious that it's just C4. So this upper bound on EXN KRS, the special case EXN K22 gives us an upper bound for this cycle on 4 vertices. So EXN of K22 by the Kovary-Sos-Turan theorem is big O of n to the 2 minus 1/2. And that's the same as EX and C4. And so we can write that as big O of n to the 1.5. So we have the Turan number of the cycle of order 3 exactly. We have an upper bound on the Turan number of the cycle of order 4. On the next slide, we're going to show a matching lower bound for the Turan number of the cycle of order 4, matching up to a constant factor, I should say. So we're going to show an omega of n to the 1.5 bound for the Turan number of C4. We're also going to look at some more odd cycles besides C3, and we'll discuss what's known about the other even cycles besides C4. So before we do this lower bound, I should erase these pictures. And for this lower bound, we're going to use a result from number theory. Suppose that P is a prime number. Just to review what a prime is, we're saying that P is greater than 1, P is an integer, and the only divisors of P are 1 and P. So that's what it means for P to be prime. Right here, A does not equal 0 mod P. What does that mean? It means that A is not a multiple of P. In general, more generally, the statement x equals y mod P, this means that P divides x minus y. So saying A does not equal 0 mod P is saying that P does not divide A minus 0. In other words, P does not divide A. And if P does not divide A, that's the same thing as saying that A is not a multiple of P. So this congruence, AX equals B mod P. So using this statement up here, that's equivalent to P divides AX minus B. And the claim is that there is a unique solution to that congruence. X mod P is our solution. So I claim that we can find an X which satisfies AX equals B mod P as long as A is not a multiple of P. And the X we find will be unique. So there's only one X we can find, but we're guaranteed to be able to find at least one X, and it will be the only X. So like we did in some other videos, we're going to construct a graph. This time we're going to construct a graph on pairs of integers. We're going to draw these pairs from this set, which is a Cartesian product. We're taking the Cartesian product of the integers 0, 1, 2 up to p minus 1, and we're squaring it. And so that gives us ordered pairs where both A and B are from the set 0, 1, 2 up to p minus 1. Now, we're going to exclude one of these pairs. So we're going to exclude the pair AB equals 0, 0. So we're taking all of the pairs except for that one. So the total number of pairs is just going to be the size of this Cartesian product here. The size of that Cartesian product is just the size of the original set right here squared. And the size of the original set, since it goes from 0 to p minus 1, it's going to have size of p. So when we square it, when we take the Cartesian product, that's going to have size p squared. And we're excluding this single pair, this 0, 0. So we had p squared pairs, but we're excluding one. So that gives us a total of p squared minus 1 pairs after we exclude that one. And those pairs are our vertices. So I just want to emphasize here, the pairs are the vertices. So the pairs are not the edges. The pairs here are the vertices. And that means that the size of our vertex set is going to be the size of the Cartesian product right here, and then minus 1 for this one. So we get p squared and then minus 1. That's the size of our vertex set. So we have a vertex set, but we haven't said how we're drawing the edges in our graph. So let's talk about that. So we will put an edge between the vertices. So we have two vertices here, a vertex AB and a vertex CD. And we'll put an edge between those vertices only if A times C plus B times D equals 1 mod P. In other words, P divides AC plus BD minus 1. So we'll only put an edge between A, B, and CD if that equation is true, that modular equation. And I claim that each vertex AB has degree at least p minus 1. And so I like to discuss this with two cases. So to find the degree of the vertex AB, we want to find the number of solutions CD for AC plus BD equals 1 mod P. Why is that? Why is that related to the degree? Well, it's because we put edges between AB and CD only if AC plus BD equals 1 mod P. So if we want to know the degree of AB, we want to know the number of edges that include AB, which means we want to know the number of solutions, CD, for the equation which defines the edges. AC plus BD equals 1 mod P. So to find this number of solutions, we can consider two cases. Case 1 will say B does not equal 0, and this will be mod P. And case 2 will be B equals 0 mod P. So case 1 and 2 will cover all possibilities. So for case 1, if B does not equal 0 mod P, let's see if I can move the case 2 down. That's good, okay. So for case 1, B does not equal 0 mod P. That means we can take this equation we're trying to solve, AC plus BD equals 1 mod P, and we can subtract the AC from both sides. So we get BD equals 1 minus AC mod P. And now we can look at this second bullet here. So the second bullet, what does it say again? If P is a prime and A does not equal 0 mod P, the congruence AX equals B mod P has a unique solution X mod P. Here we're applying it to the coefficient B instead of A. So the A up here is a B down here. The variable X up here, this X, is now a D. And we can treat the A and the C here as fixed. So what does this tell us? Well, we can take any possibility for C, any possible C, and this will give us a unique solution for D. So any of the possibilities for C from this set, 0, 1, 2 up to P minus 1, we can put each of those in for the value of C right here. And recall the A and the B are fixed. So both this A and the B, these are fixed. And this C right here, so the C has a total of P possibilities. And those possibilities are 0, 1, up to P minus 1. So each possible C, we can put in this equation with the B and the A fixed. And since B does not equal 0 mod P, we can find a unique solution for D. So in case 1, when B does not equal 0 mod P, there are at least P solutions for C comma D. So case 1, we got at least P solutions for C comma D. Case 2, let's see how many solutions we get for C comma D. So for case 2, if we have B equals 0 mod P, we know that AB can't equal 0, 0 from this third bullet. So that means that A does not equal 0 mod P. And so we can do something very similar to what we did in case 1. We can take our equation AC plus BD equals 1 mod P. And we can write it as AC equals 1 minus BD mod P. And we can let D take any possible values. So there are P possible values for D. And we can use this second bullet again, the same second bullet here. And this time we can use it with A as the coefficient of the variable. And our variable here is C. So the X is C in this one. And C is uniquely determined by A, B, and D. So we get, for any of the P possible values for D, we get a unique solution for C. So again, with case 2, we get at least P solutions for C and D. We just argued it in the opposite order. We did D and then C instead of C and then D. So for both cases, regardless of whether or not B is 0, we get at least P solutions for CD to this equation AC plus BD equals 1 mod P. Now it's possible that one of the solutions, it's possible to get this solution CD equals AB. So it's possible that that is one of the solutions. For example, if A equals 0 and B equals 1, that would be a solution. We would get CD equals AB as one of our solutions because A squared plus B squared in this case is 1 mod P, regardless of what P is. So sometimes we'll get this solution, CD equals AB, and we don't want to put an edge there. So when we assign the edges of our graph, we only put an edge between distinct vertices, A, B, and CD. So we don't have any self loops. So no self loops. So at most one solution, CD. So at most one solution, CD, is going to be AB. So we have to exclude that solution from our count for the degree because AB cannot be a neighbor of itself. So instead of getting P, we got P minus 1 for the cases when we have to exclude the solution A comma B. There will be cases when we don't get A comma B as a solution, but for the cases where we do get it, we can say even in those cases, the degree of every vertex is still at least P minus 1. And so that's what's stated in this bullet with a lot more explanation. So I should probably clear a lot now so we can see the next few bullets. And what I've written in this bullet is just the explanation I did for case 1. And case 2, as you saw, was symmetric to case 1, just with the C and D, the order reversed. So let's recap the information that we have here. So we saw that the size of the vertex set V was P squared minus 1 because it's the size of this Cartesian product, P squared, excluding the order pair 0, 0. We also saw the minimum degree of the graph is at least P minus 1. And so that means we know the number of edges times 2 is equal to the sum of the degrees. So we can use this, we can divide both sides by 2. And that tells us that the number of edges is at least the number of vertices, so the order of our graph, times the minimum degree over 2. And that's how we got P squared minus 1 times P minus 1 over 2. So we have the order of the graph, we have the number of edges in the graph. Now we just want to see, why does this graph avoid the cycles of order 4? So in order to see that, we could assume that we have some cycle in our graph, and we can draw a picture of it. So we have A comma B here. And let's say we have a C comma D down here. And then we have two vertices which are both neighbors of AB and CD, an XY and a ZW. So there we've drawn it as a cycle. We can also think of it as like a K2-2. So there's our A comma B, C comma D, XY, and ZW. So these are the same graph. And if we have a C4 in G, that means that AB, CD, XY, ZW are some 4 distinct ordered pairs for which we have edges AB to XY, AB to ZW, CD to XY, and CD to ZW. So what does that mean in terms of our rule for edges? It gives us a total of 4 modular equations. So there's 2 of them. So for our edges from A, B to XY and CD to XY, we get the equations AX plus BY equals 1 mod P and CX plus DY equals 1 mod P. We also have these equations for the AB, CD, and the ZW. So we can say AZ plus BW equals 1 mod P. That's because we have the edge AB to ZW. We can also say CZ plus DW equals 1 mod P. And that's because we had this edge from CD here to ZW. And here's a problem for you to think about. Prove that the system of equations AX plus BY equals 1 mod P and CX plus DY equals 1 mod P, so the one in this bullet right here, has at most one solution. And I just want to note that I'm talking about a solution for X comma Y. So it's a system of equations with 2 variables. So we're treating the A, the B, the C, the D as fixed, and our variables are X, Y, and it's one solution, mod P. Everything here is mod P, so I didn't write the mod P, I just wrote one solution, but since these are modular equations, we're talking about solutions mod P. And so I'd like you to prove that AX plus BY equals 1 mod P and CX plus DY equals 1 mod P has at most one solution for XY mod P. And that means if we look at this system of equations in the second to last bullet, it's the exact same system that we see in the third to last bullet, except Z in place of X and W in place of the Y. So that's the only difference with the previous bullet. So if we're saying that the system of equations has at most one solution, we're saying that the XY would have to equal the ZW. If there is a solution XY and there is a solution ZW, then XY has to equal ZW. And that would be a problem with this picture we drew up here and this one. Same issue with both of them. The issue is that we were assuming that X, Y, and ZW are different. We drew them here, they're different vertices, and that can't be. So by this problem for you to think about, we can't have X, Y, and ZW being different vertices. They're actually the same vertex. So we never had that C4 slash that K22. So our graph G, it actually is C4 free, but you just have a little work there in that problem to show that actually these solutions X and Y and Z and W, they're actually just the same solution, X and Y. And that's exactly what I just put in that bullet at the end too. So we're trying to prove that these two, X, Y, and ZW, they actually are the same thing. So if they're both solutions to the system, so they're both solutions to the same system here with the X and Y, same system there with the Z and W, and just prove that they're actually the same ordered pair. So let's recap what we've done. So we constructed this graph. We just saw it C4 free, and we also saw that it had order p squared minus 1, so it had p squared minus 1 vertices. And the number of edges is at least this, at least p squared minus 1 times p minus 1 over 2. So I should have a greater than or equal to there, because we only said it's at least that. We didn't say it's exactly that. And there's this useful fact from number theory, another useful fact, known as Bertrand's postulate. And what it says is for every integer n greater than 1, you can always find a prime p such that n is less than p is less than 2n. So I claim you can use this postulate combined with the construction we just used to prove the lower bound on the Turan number of C4. And I leave that as a problem for you to think about. Prove that this extremal function, the Turan extremal function of n comma C4, is equal to omega of n to the 3 halves. And I'll just note that this also gives us the lower bound on the Turan number of the complete bipartite graph, K22. It also gives us K2s for any s greater than or equal to 2. So from this result, if ex of n comma K22 equals omega of n to the 3 halves, then we know immediately that ex n comma K2s has to equal omega of n to the 3 halves for any s greater than or equal to 2. And this is because of a fact that we observed when we started talking about the Turan numbers. It's because K2s contains K22. So we actually did something more than finding a sharp bound up to a constant factor on the Turan number of C4 and K22. We have a sharp bound up to a constant factor on EX and K2s. And this is for any s greater than or equal to 2. So we can say this is theta of n to the 3 halves. So we already proved the upper bound. The upper bound was just the Kováry-Solis-Turan theorem. We proved that with Jensen's inequality. And the lower bound is just as we explained right here. So you get this n to the 3 halves lower bound. And I'll note right here that the constants in our bound depend on s. And s must be a constant for this to be true. So s has no dependence on n. So now that we have seen C4 and some more complete bipartite graphs, let's move on to some odd cycles. And there is another bullet on the slide, but it's pretty much what I just said. So nothing more to say really. So in order to discuss the Turan numbers of odd cycles, let's review what is the chromatic number of a graph. So if you have a graph G, the chromatic number of G, which we write as chi of G, is just the minimum number of colors required to color the vertices of G so that no two adjacent vertices have the same color. So before we apply the chromatic number to bound some Turan numbers, let's look at the chromatic numbers of some special families of graphs, just to illustrate the definition. So the chromatic number of the complete graph of order n, Kn, this is n. This is because if you have any two vertices in your graph of the same color, since there's an edge between them, that would not be a proper coloring. You can't have any two vertices be adjacent with the same color. So this is why you need all different colors for all the vertices. So chromatic number has to be n for that one. And obviously it's at most n because there's n vertices. For the star K1n, so this one we can draw. So we have a center vertex, and then we have a bunch of leaves. And I claim for this one, the chromatic number equals 2. So we know since n is greater than or equal to 1, there's at least one edge. And since there's at least one edge, that means that the two vertices in that edge have to have different colors. So the chromatic number is at least 2. And we can see that it's at most 2 because we can take colors red and blue. We can color the center red. We can color all the leaves blue. And that gives us a valid 2 coloring, which is proper. We can also look at the path Pn. So this one I can draw as so. And for this one, as long as n is at least 2, we'll have the same thing. We'll have at least one edge. So that means our chromatic number will have to be at least 2. And we can use a red-blue coloring. We can just go red, blue, red, blue, red, blue, and so on. And that gives us a valid 2 coloring of the vertices, which is proper. Let's consider another one, which is going to be more relevant to our discussion in this video. So the cycles Cn, and we're assuming n is greater than or equal to 3 so that we don't have a degenerate cycle. So our cycle is an actual cycle. So if n is even, I claim in that case the chromatic number is going to be 2. So it's at least 2 for the same reason as the last 2 bullets. There's at least one edge in there. And if it's even, so I'm going to draw an even one. So even though proof by example is not a valid proof, but this example illustrates the idea completely. You can generalize the idea to any number of vertices in the cycle. So we have some even cycle right here. And we're just going to label them RB, RB, like we did on the path, RB, RB. And it works out because the number of vertices in the cycle is even. So we don't get any 2 adjacent ones of the same color. Now, what happens when the cycle has odd length? So I'm going to draw a picture of an odd one. So first, since we know n's at least 3, and our cycle has odd length, we know there's an edge in there, so the chromatic number is at least 2. And we have an odd length cycle right here. So we can try to do it with 2. And if it doesn't work with 2, then that'll tell us that it has to be at least 3. And then if we can find a coloring with 3, that'll tell us it's 3. So let's see if we can see why it doesn't work with 2. So assume for contradiction that it does work with 2. So we'll just pick a vertex and assign it a color. Without loss of generality, we'll say it has the first color. It will be red. Doesn't matter if it's red or blue. Just without loss of generality, it's red. Now, since this is a proper vertex coloring, the 2 adjacent vertices of this one must have different colors to it. So this one must be blue, and this one must be blue. Assuming we're doing a 2 coloring here, our only colors are red and blue, so they both have to be blue. Now, we can use that same rule we just used about proper colorings. Any of the adjacent vertices have to have different colors. So this neighbor of this blue one has to be red, and this neighbor of the blue one has to be red. And we can keep it going like this. So the neighbor of the red one has to be blue. The neighbor of this red one has to be blue. And then we have a problem here. Our coloring is not proper. And all we did is we assumed that this vertex right here was colored red. If we assumed that it was colored blue, then these 2 would have been red, these 2 would have been blue, and these 2 would have been red. So regardless of that original vertex, we still end up with 2 adjacent vertices of the same color. And regardless of how long our cycle is, as long as the length is odd, we will always have the situation with 2 colors. If we try to use two colors, we are guaranteed to have 2 adjacent vertices of the same color. So we know that the chromatic number of Cn, it's greater than 2. It's strictly greater than 2 if n is odd. And we can see that it's less than or equal to 3. So why is it less than or equal to 3? Well, we can take this one here that gave us the issue because it was blue and this one was blue. And we can just let that one be the third color. We'll say the third color is green, G. So instead of a B, we use a G there, and that fixes everything. So the chromatic number of a cycle of odd length is going to be 3. And so now we're going to apply chromatic number to bounding Turan numbers once I clear this. And we're going to use this very famous theorem from extremal graph theory called the Erdos-Stone-Simonovits theorem. And here's what the theorem says. And it gives us a bound on the Turan number of a graph H in terms of the chromatic number of H. And this bound is very sharp as long as the chromatic number is greater than 2. So here's the bound that we get. For any graph H and fixed epsilon greater than 0, there exists an integer large n such that for all little n greater than large n, we have these upper and lower bounds on the Turan number of H. So the extremal function of n comma H. We have a lower bound of 1 minus the chromatic number of H, or 1 minus 1 over the chromatic number of H minus 1, and then that minus epsilon times n squared over 2. That's our lower bound. Our upper bound, we have the same beginning of it, 1 minus 1 over the chromatic number of H minus 1, but then we're adding an epsilon. So I just want to point out the difference here. We have a plus here, we have a minus here. That's the only difference between these upper and lower bounds. And we still have that n squared over 2. So first thing to note here is that if the chromatic number of H is greater than 1, so if it's greater than 2. So if the chromatic number of H is greater than 2, then we can say that 1 minus 1 over the chromatic number of H minus 1, this is going to be greater than 0. And clearly it's also going to be less than 1. So we can put these bounds on it. And so as long as the chromatic number of H is greater than 2, we can say that EX of NH is approximately 1 minus 1 over the chromatic number of H minus 1. And this just times n squared over 2. So as long as the chromatic number of H is greater than 2, then this quantity that we have right here, the 1 minus 1 over chromatic number of H minus 1, this is going to be between 1 and 0. So an upper bound of 1, a lower bound of 0. And it's going to be strictly between them. So it'll be strictly greater than 0. So we get some real number times n squared over 2. Now, if chromatic number of H equals 2, this bound is not so great, because in that case we get 1 minus 1 over the chromatic number of H minus 1 equals 0. So in that case, the theorem is telling us that negative epsilon n squared over 2 is less than or equal to EXNH is less than or equal to epsilon times n squared over 2. And so it's saying that that's true for any fixed epsilon greater than 0. So we can make epsilon arbitrarily small. So all this is telling us is that EX of NH equals little o of n squared. And we already knew this from the Kováry-Solis-Turan theorem. So the reason why we know that is because if we have a graph of chromatic number 2, chromatic number 2 means that we can red-blue color it. If we can red-blue color our graph, we can put the red vertices on the left, the blue vertices on the right, and all our edges have to go from red to blue. We can't have any edges going between two reds or between two blues. And this is a bipartite graph. So any graph that has chromatic number 2 or chromatic number 1, you can draw it as a bipartite graph. It is a bipartite graph. And we know any bipartite graph, so any bipartite graph we can say is contained in KRS for RS sufficiently large. So we can use our upper bound from the Kovarisov-Turan theorem to get a stronger upper bound than this little O of n squared. So when we have graphs of chromatic number 2, in other words, bipartite graphs, this upper bound is not useful. And same with the lower bound, it's even less useful because it's saying that the Turan number is at least a negative number. And we already knew that because it's non-negative. Okay, so I'm going to erase a little so we can see the rest of the bullets. So like I said before, this gives us very sharp bounds up to the coefficient of the n squared. So we know what the coefficient of the n squared is in these bounds for EXNH whenever the chromatic number of h is greater than 2. So we know EXNH for all of these h is theta of n squared, as long as chromatic number of h is greater than 2. But it's a much stronger bound than that. So it's actually giving us the coefficient of the n squared in this bound. So our coefficient of the n squared is this quantity here that we see on both sides. And we can make the epsilons. This is any fixed epsilon greater than 0. So we can make them arbitrarily small. And like I mentioned before, this bound is useless for the graphs with chromatic number 2, which is bipartite graphs. So any graph with chromatic number 2, as we saw, we can draw it as a bipartite graph. And any bipartite graph, this one also clearly has chromatic number at most 2, because if you have a bipartite graph, so we have a bipartite graph here, all the edges go from left to right. We can color these all red and we can color these all blue, and that's a 2 coloring. So clearly bipartite graphs have chromatic number most 2, and any graph of chromatic number 2 is a bipartite graph. And that's what I note in this last bullet here. So in order to see why this theorem is true, this theorem that I state here, for any graph h and any fixed epsilon greater than 0, there exists some large n, such that for all little n greater than large n, we have these sharp bounds on the Turan extremal function of h. So we can bound it between this lower bound, that constant minus a small epsilon times n squared over 2, and this constant plus little epsilon times n squared over 2. And we're not going to go through the full details of the proof. We're just going to discuss the main idea of why this is true. And so in order to discuss that, we're going to define this graph that we've actually seen before. So this graph TRT, it's obtained from the complete graph KR of order R, and we just replace each vertex in the complete graph with an independent set of T vertices. So let's draw a picture to see what's going on. So we'll take, let's say, T of 3, 2. So we'll start with K3. That's our KR. And then we're going to replace each vertex with an independent set of vertices. So 2 vertices without an edge between them. Maybe let me draw them a little more evenly, horizontally. Okay. And then this vertex will replace with 2 vertices, no edge between them. Same with this one here. It's now 2 vertices. And then, okay, so we have these independent sets of T vertices for each vertex that we had originally. And we'll replace each edge UV with the T squared edges UIVJ for each 1 less than or equal to I less than or equal to t, 1 less than or equal to j less than or equal to t. So we take this edge right here from u to v, and then we have like our u1, v1, u1, u2, and we have v1, v2. And let's say down here we have a w1, w2, and that's our w. So we have edge u1 to v1, u1 to v2, u2 to v1, u2 to v2. And our uw edge gives us u1 to w1, u1 to w2, u2 to w1, u2 to w2. And then the vw edge, we have v1, w1, v1, w2, v2, w1, v2, w2. And we can do this with any complete graph and any t value. So we can build this graph TRT. And this is the part that we're not going to prove. So we're going to use this fact without proof. And we're going to see why the Erdos-Stone-Simonovits theorem is true based on this fact. So from this fact, we're going to prove the theorem. And the fact that we're claiming without proof is this right here, that the Turan extremal function of t of r plus 1 comma t. So we're taking the complete graph of order r plus 1, kr plus 1, and then replacing vertices with sets of t. And the claim is that the Turan extremal function of that graph is less than or equal to 1 minus 1 over r plus epsilon times n squared over 2. And I'm just going to note here that this, when we have t equals 1, this just tells us that ex n comma kr is less than or equal to 1 minus 1 over r, kr plus 1, sorry, kr plus 1. So that was a t of r plus 1 comma t. So kr plus 1, this is going to be less than or equal to 1 minus 1 over r plus epsilon times n squared over 2. So this is an approximate form of the Turan theorem. And we proved the Turan theorem in another video. So we proved a sharper form of this bound for complete graphs. But this is a more general bound than complete graphs because this is for any of the graphs t of r plus 1 comma t. So we only get a complete graph when t equals 1. Any of the others are not complete graphs. But they still have approximately the same bound as the corresponding complete graph. So the bound we got for the complete graph was approximately 1 minus 1 over r times n squared over 2, the complete graph of order r plus 1. So this bound, we see it's the only difference is this plus epsilon. And so we want to use this fact to see why the Erdos-Stone-Simonovits theorem is true. And so that's the question in that bullet. Why is the Erdos-Stone-Simonovits theorem true? And so for the lower bound, we can use the graph TRT that we just defined. And we've actually seen this graph in class earlier. And we'll use it with r equal to the chromatic number of h minus 1. And t will equal the floor of n over r. So this graph, it's going to have, so we start with a kr, and then that goes to r independent sets of size t. And we can see in that graph that the number of edges, we can prove a lower bound here. So the number of edges is going to be approximately r, choose 2, and then times t squared. And so this is approximately r times r minus 1 over 2 times n squared over r squared. And so we get r minus 1 over r times n squared over 2. And this I just want to know is an n. It's an n. Let me make that more legible. There we go. Okay. And so that we can see gives us the lower bound we want if we take r equal to the chromatic number of h minus 1. Because we can write this right here as 1 minus 1 over r times n squared over 2. And so if r equals chromatic number of h minus 1, then this gives us exactly the lower bound we want. And the minus epsilon, why is there a minus epsilon? Well, that's what happened with this approximate right here, because the t squared, it was floor of n over r squared. So it's not exactly n squared over r squared. It's slightly less, but the epsilon is going to be a little o of 1 with respect to n. So it's making barely any difference in the bound to have this floor function. So that gives us the lower bound. We can just use this graph TRT. Now, we need to see that this graph avoids our graph H. So why is TRT? Why is that H free? And we can see that pretty quickly. So we can see that if we take a subgraph of TRT, any subgraph has chromatic number at most r. And this is because TRT itself has chromatic number of r. So TRT, we can color each of the independent sets a different color, and that gives us a valid r coloring of TRT. So the chromatic number of TRT is at most r. That means any subgraph has chromatic number at most r. And that means that H cannot be a subgraph because H has chromatic number of r plus 1. So since H is not a subgraph, that means that TRT avoids H. So I'll just note that right here. TRT avoids H since H is not a subgraph. Okay. And as I noted down here, the number of edges in TRT is approximately 1 minus 1 over r times n squared over 2. And that's exactly what I wrote right here. So that was just a little more explanation than I put in the bullet. Okay, so now to see the last bullet, I'm going to erase. So the upper bound. In order to see the upper bound, this is a problem for you to think about. And I meant to write problem here, but I didn't write it, so I'll write it here. So a problem for you to think about. And this one is pretty straightforward. Prove that if H has chromatic number chi of H, then you can embed H in this graph TRT with R equal chi of H. So prove that you can find a copy of H in this graph T of chi of H comma T as long as T is sufficiently large. So when you're proving this problem, when you're proving that you can find some T of chi of H comma T for T sufficiently large that contains H, you just want to say what the value of little t is for which you can find H in there and just prove that you can find the copy of H. So you can just construct the copy of H if you want. And so I claim then, if you prove, so this problem that's left, to prove that if H has chromatic number chi of H, then H can be embedded in this graph T of chi of H comma T for T sufficiently large. That tells us that T of chi of H comma T contains H for T sufficiently large. And what does that mean? Well, then we can use the fact that EX of NH is less than or equal to ex of n comma t of chi of h comma t. And we can apply this upper bound, the one that we state without proof. And that upper bound, from there, we can say this can be less than or equal to 1 minus 1 over chi of h minus 1, and then plus epsilon times n squared over 2. So we're just applying this bound from this bullet, and we're only applying it to t of chi h comma t. So we're using r plus 1 equals chi of h in that bullet, in this bullet up here. And so that means r equals chi of h minus 1. So that's why we got this right here. And we can see then that this is exactly what we were trying to prove, the upper bound right here. So this is the exact upper bound. So that's why the Erdos-Stone-Simonovits theorem is true based on this fact here. So really, all of the work of the proof boils down to this fact that we didn't prove, but you see that this fact implies this full theorem. So even though this seems like a much weaker fact, it's only about this family of graphs T, RT, it gives us this theorem about all graphs of chromatic number greater than 2. So we're going to look at a few corollaries of the Erdos-Stone-Simonovits theorem. So like I mentioned before, for any graph H where the chromatic number is greater than 2, we have sharp bounds on its Turan number now, up to the coefficient of the n squared. So we know what the coefficient of the n squared should be. In particular, we can discuss the odd cycles, all of them now. So we already knew C3, but all of the others, we know their chromatic number. So we know that if n is odd and n is greater than or equal to 3, then the chromatic number of Cn equals 3. So this is one of the graphs where we have sharp bounds on its extremal function up to the coefficient of n squared because the chromatic number is greater than 2. So in particular, I'm leaving that as a problem for you to think about, is to find the limit as n goes to infinity of the extremal function of n comma c of 2k plus 1 divided by n squared, and do this for each k greater than or equal to 1. So k equals 1, that's a C3. And for C3, we saw that ex n comma C3 was approximately n squared over 4. So this limit for k equals 1, exn C3 over n squared, we saw that limit is 1/4. We already proved this. So this proof, you need to do this for all the k greater than 1. So we already know it for k equals 1, but you got to do it for the other k values. But you can use anything that we stated in this video. So anything from this video, you're free to use. So that brings us to the end of the first half of this video. Thanks for watching.